All right, so in this video, we're going to look at a second combustion analysis example. One difference between the previous example is that in that previous example, our compound only had carbon and hydrogen, and in this example, the compound has carbon, hydrogen, and oxygen. The other difference, in the last one, they only wanted the empirical formula. In this case, we want to find the molecular formula. And so to do that, they've also given the compound's molar mass. But we'll do that in exactly the same way that we found the molecular formula in our problems where we were just determining the empirical formula from mass percentage data. So we'll worry about that at the end. The first thing we need to do is find the empirical formula. So as with the last example, if we can find the moles of carbon dioxide, that's going to be equal to the number of moles of carbon that was in the original compound. And so I need the molar mass of carbon dioxide. And so for CO2, and so I'll take my mass of carbon dioxide, and I'm going to write out an extra step. I didn't write this step last time, but I'm just going to show that right for every 1 mole of carbon dioxide, we get 1 mole of carbon atoms in the original compound. And when I do that math, I get 0.9 moles of carbon. And we want to do the same thing with the water. All of the hydrogen in our original compound is converted into water, but in that case, for every 1 mole of water, I get 2 moles of hydrogen atoms. So I'll have a 1 to 2 ratio for the hydrogen. So for water, its molar mass divided by the molar mass. And now for every 1 mole of water, I'll get 2 moles of hydrogen atoms. And that comes out to be 1 mole of hydrogen. So I'm going to take this and go on to the next slide where we have a little bit more room to find then the moles of oxygen. All right, so from the previous slide, we found the moles of carbon and the moles of hydrogen. To find the moles of oxygen, what we need to do is, this is the total mass of the compound. We can find out how much 0.9 moles of carbon weighs, how much 1 mole of hydrogen weighs, subtract that from the mass of the compound, and so whatever mass is remaining, that's the mass of oxygen. Then use the molar mass of oxygen to turn that into moles. Then once I have the moles of carbon, hydrogen, and oxygen, I'll find the ratio to get the empirical formula. So the mass of carbon times its molar mass, and I get 10.81 grams of carbon, 1 mole of hydrogen times its molar mass, 1.01 grams of hydrogen. And so now take the total mass of the compound, subtract the mass of carbon, subtract the mass of hydrogen, and I'm left with 1.6 grams. And so that's the mass of oxygen. All right, so I need to convert that into moles. So grams of oxygen divided by the molar mass of oxygen. And I get so now I know how many moles of each element I have. Right, I have 0.9 moles of carbon, 1 mole of hydrogen, and 0.1 moles of oxygen. So at this point, to get the empirical formula, I just want the ratio of the number of moles of each element. So I'll divide by whichever element I have the least moles of. So that'll be the hydrogen. I'm sorry, that'll be the oxygen. So divide each one by 0.1. And I get 9, 10, and 1. So my empirical formula is C9H10O. So one more part to the problem. We have the empirical formula, but now we want to find the molecular formula. And so I'll finish this off on the next slide. All right, so we said the empirical formula was C9H10O. And so to find the molecular formula, I know it's going to be some multiple of the empirical formula. And to find out what that multiple is, I'm going to take the molecular mass or the molar mass and divide it by what I call the empirical mass or the molar mass of the empirical formula. So to get what I call the empirical mass, I'll do 9 times 12.01, 10 times 1.01, plus 16. And for that, I get 134.19 grams per mole. So to find the multiple is the molar mass over the empirical mass. So I'll take the 268.34 divided by 134.19, and I get 2. So the molecular formula is twice the empirical formula. So my molecular formula then is C18H20O2. And that's our final answer.